In this video, I'd like to continue our practice with factoring large polynomials using synthetic division. And even though I'm only going to walk through probably just one example in this video from this group, as well as an applied example down below, I would like for you to select, a handful of problems here, 4 or 5, maybe all of them to complete on your own. And come see me for clarification if you're not quite sure if your approach is strong enough or correct for these given polynomials. Because your analysis on these polynomials is essentially what your 5th unit test is going to be over, or at least part of the unit test will be over. So we're going to go through several steps for these types of problems. We're going to identify the possible rational roots using the rational roots theorem. We'll determine the actual rational roots, and we will use a calculator to do so. We'll factor the polynomial and solve for the remaining roots. We'll identify the y-intercept, and then finally sketch the polynomial based on end behavior, multiplicity, known zeros, and the y-intercept. So while we're here, we might as well just go ahead and try one of the more challenging problems, and it appears that maybe 48 might be challenging. But in actuality, that one's not as complicated as number 44, I would say. Because remember, to identify the possible roots, we need the factors of our constant and the factors of our leading coefficient divided by one another in order to create a list of potential rational roots. Down here, there are only a couple factors of 8, and there's only one pair of factors of the number 1, so that list is pretty small. When we create the list of factors of 28 and 3, however, you're going to see a much larger list. So let's go ahead and do that. For the p-value of 28 and a q-value of 3, well, the q-value of 3 produces just positive and negative 1 and 3. Those are the only factors of the number 3. For 28, however, we'll have positive and negative factors, and we know that 1 and 28 work. If there are any additional factors, they have to be between 1 and 28. I know that 2 and 14 also factors 28. If there are any more, they have to be between 2 and 14. 3 does not go into 28, but 4 does. 4 times 7 equals 28. And if there are any other factors, they'd have to exist between 4 and 7. I know that 5 and 6 does not go into 28, so we now have a complete list of factors. And this set of solutions right here would satisfy question A. Oops, no, I'm sorry. I take that back. I'm getting ahead of myself here. This produces our factors of P and factors of Q, but in order to answer part A, we need to take the factors of P and divide them by factors of Q. So this list is going to be a bit larger. And so we know that 1 through 28 from the list of P when divided by the number 1 is just going to repeat itself. So I know positive and negative 1, 2, 4, 7, 14, and 28 are potential zeros, as are each of these numbers divided by 3. So when we think of unique results, that's going to be 1/3, 2/3, both positive and negative of each of these. That's why I put my positive and negative sign in front of the grouping symbol here. We'll need 4/3, 4 divided by 3. We'll need 7/3, 14/3, and that can't be reduced. Even if it could, we would check to see if that's a repeated result. And then finally, 28/3. So now this list satisfies question A. All the potential rational roots exist within this list. If there are any rational numbers that will solve this original polynomial, that is, make the polynomial equal to 0, they will exist somewhere in this list. Now remember, and this is the equation that we would be solving with the numbers from this list, but I do want you to remember that there could be other real and non-real numbers that solve this equation. But as far as the rational numbers within the real number subgroup, they have to come from this list. And while we're here, we might as well make a note. There are only 3 solutions to this equation, 3 real number solutions to this equation. Actually, let me rephrase that. 3 solutions in general. They don't even have to be real numbers. But if the solutions are rational, they will exist in this list. If they're not rational but still real, we'll have to find them with some other techniques. So as far as finding the rational number solutions, we need to test these numbers inside of the equation. And so I'm going to use the TI-Nspire to do that. I'm not going to use the graphing component. I don't want you to use the graphing component. Instead, I want you to use just shortcuts using functions and stored variable values. And we're going to investigate the function at 1, the function at -1, the function at 2, -2, and so on. And it sure would be nice to find 3 solutions within this list before we get to the end, but that doesn't always happen. So, we'll be on the lookout for it, but it's not guaranteed to occur. So I'm just going to start with this list here, maybe 6 or 8 problems to 6 or 8 values to investigate first. I'm going to reach for my calculator now that I think it's started up, and we'll set up this calculator to make this go a little bit more quickly. Now, I showed this in the other video, and I do expect you to be able to complete this on your own when we take our next test. I'm going to rewrite the equation, but this time I'm going to use the letter a as our variable. So we've got 3a cubed minus 7a squared. Whoops, let me try to put that in the correct position. So minus 7a squared plus 12a minus 28. And I'll just press enter here so that that expression is essentially stored in memory. Now I need to store the value 1 in place of a. So I press 1, control variable to recall the store command, and then I'll type the letter a. Now the letter a is stored in place as the number 1. When I copy the equation above by highlighting it and pressing enter, it copies down, and we've got a result. Now what we're looking for are function results that end up equaling 0. And if they don't equal 0, I don't really care what the number is, although I may ask that you illustrate that so that I know that you're not using your graphing calculator to generate the image here. Again, our objective is to perform an analysis on this equation without the use of a graphing tool. Even though we're using a graphing calculator, we're not using its graphing capabilities. So by writing down these numerical results, I'll know that you at least performed the analysis algebraically. So I'm going to evaluate the number 2 at a. So we'll store it first and then reevaluate the function. No solution there. So I'm going to keep this process going until I find a 0. Now I'm only partially through the list, but I thought I'd jump in and point something out to you here. If you notice as you're starting to check your numbers, and we've only made it this far, positive, negative, 1, 2, 4, and 7, but you'll see that by the time we get to number 7, these results are really starting to explode and run away from one another. Chances are you're not going to find a 0 at these 2 positions, so if you want to temporarily skip those in the hopes of finding them elsewhere, I think that would be a good approach. If you want to be methodical and continue to work through every question or every problem, that's perfectly fine too. Just keep in mind that it wouldn't be a surprise if you don't find a solution at these numbers, 14 and 28. That'll continue the pattern here. But we do have to check the function at 1/3, at -1/3, and so on. The pattern would essentially restart once you investigate this next round of values. But I thought I'd just share that with you for the time being in case you were curious. Hey, I finally found one. So that's a good sign. It took several evaluations so far, but I finally found a 0. Fingers crossed. Let's see if we can find some more in the remaining 6 or so that we've got left. Okay, so in those last 5, there were, I ended up not finding a 0, which is a bit disappointing because of all that time that was spent testing these numbers. And it wasn't fast. By no means was it fast, but that's the process that we've got at this point. I didn't find any more, but on the plus side, we can use this to potentially reduce our polynomial from a cubic to a square using synthetic division. And from there, once it's in quadratic value, we can find the remaining solutions using the quadratic formula. So that's good. All right, so we found the actual rational roots. The only one was 7/3. So we'll say x equals 7/3. And if there was a list of them, I would create a whole list, but there was only the one there. So that answers part B. Now for part C, factor and solve the rest of the polynomial. And again, we'll use synthetic division for this. So I'm going to list the coefficients. We've got 3, -2, -7. These are the coefficients from the polynomial. 3, -7, 12, and 28. Now I do want to take a side step for a second here, and I don't know if I've got any examples in this list. It doesn't look like it, but what I do want to point out, in case I forget to mention it in class, is that it's very important that we represent every term in descending order. So if I were to give you a polynomial like 47, and if it were written as x to the 4th minus 3x squared minus x plus 2, it may not be immediately obvious at first, but there's a term that's missing in this list, and we can see it. By the way, I've got it written here. There's a space where an x cubed used to be. So if I were setting up the synthetic division for this guy in this particular example after that one was missing, I'd want to represent that missing value with the number 0, because 0 is the coefficient associated with the x cubed term. Then we can move on to -3, -1, and 2. But this missing term, you got to be on the lookout for those. Anyone that's missing should be represented with the number 0. We didn't have that in this case, so we can continue to move on. Now, the math here may get a little bit tricky because the 0 that we're investigating is 7/3. So we're going to investigate 7/3 using synthetic division. I'm going to immediately bring down the 3, as I always would, and then multiply 3 times 7/3. Well, that's easy. It's just 7. I'll add those together. Now that product is easy. We'll add those two together. Now we want 12 times 7/3. Well, that's 84/3 if you were to multiply that in your head, and I don't know what 84 divided by 3 is, so I'll just cheat here and use the calculator. 7/3 times 12. This would be permissible because the calculator is permitted, just not the graphing component. And so that ends up being 28. Oops. I wonder if I've got a sign missing here because I had hoped that these two would add together to cancel out. Let's just check that here. Yep, sure enough, I missed my sign, -28. There we go. Signs are very, very important. I was lucky that I only missed one at the very end here. If you had missed one early on and then computed incorrectly the rest of the way, that could be a big problem for you. Well, let's remind ourselves what we have right now. We recognize that 7/3 is a factor of the function f of x. So I can write x minus 7/3 as a binomial factor of the polynomial. And these terms that remain, what was an x to the 4th power, x cubed, this was x cubed to begin with, wasn't it? X cubed squared, x to the 1st, and technically x to the power of 0. We now have 3x squared, 0x to the 1st power, and 12x to the 0th power. So what we're left with is 3x plus 12, 3x squared plus 12. And that's it. That's the factored result of the original polynomial. I know that this is the factored form because if it was able to be factored any further, we would have spotted rational let me try to write this down. I can't write and talk that well right now. But if there were further factors here, we would have spotted them in this list. There are no other factors, so I'm confident in stating that this result here is the factored form of the original polynomial. And with this being a pair of two binomials, if I FOIL these back together, after I FOIL them, I should end up with 3x cubed minus 7x squared plus 12x minus 28. I should see that after I FOIL it back together, and I bet I would. Now here again, the reason why we're factoring those, we want to find the remaining zeros. We know that when the factored form of the polynomial is set equal to 0, then each of the factors themselves could be set equal to 0 in order to solve. And this one, we already know what's going to happen when x minus 7/3 equals 0. Then x in and of itself is going to be positive 7/3. We knew that solution from a little bit earlier. Put a red box around that. The other one we would set equal to 0 as well, and we actually get pretty lucky here. 3x squared plus 12 equals 0. Since there's no b value in this quadratic, we can actually solve this using square roots. If there was a b value, then I would use the quadratic formula. But I'm not going to use the quadratic formula here because I can subtract 12 from both sides. I can then divide by 3 and then take the square root of both sides. Now remember, since I'm going to be taking the square root and I'm putting that down on paper, it wasn't here to begin with, then I have to be prepared for both a positive and negative answer. And the positive and negative form of the square root of -4 is simply positive and negative 2i, two solutions that are complex or imaginary numbers. So since part C asks us to factor the polynomial and solve, well, we do have the factored results and we have the remaining solutions. And as I said before, there are 3 solutions to this equation. We knew that there would be 3, and as it turns out, one is a real number, rational solution, and the other 2 solutions are imaginary or complex. So let's move on to part D. Identify the y-intercept. Well, that's easy. The y-intercept occurs when x is equal to 0. And so if x was equal to 0 and we were to change all of these x's to 0, then these 3 terms disappear. The y-intercept is -28. We also mentioned that in a prior video that the y-intercept is always our constant value at the end. So we've got a y-intercept of -28. Now we should have enough information to sketch this graph. So if I put together an xy axis, scaling won't be incredibly important here, but the sketch should be representative of the behavior of the function. We do have a y-intercept down here somewhere, and that's approximately -28. We have an x-intercept at 7/3. Now 7/3 is 2 1/3, so I'm just going to put the dot right about here. And I may even indicate that this position is -28, just for clarity. But we've got an x-intercept at 7/3. We have a y-intercept at -28. Because there's only one real number solution, I know that the graph will not touch the x-axis any more than this. I also know that since we have a positive leading coefficient and an odd degree, that the right tail has to point up and the left tail, which actually emanates from this 0, has to point down. It does have to go through this point, so I'm going to make sure that it kind of turns down and away from the x-axis. I don't want it to curve like this, because then that would imply that it will eventually turn back upwards, which we know it can't do. There are no other zeros in this graph. And so right tail is pointing up, left tail eventually points down. It goes through the y-intercept at -28, and I think this would be a pretty good representation of the behavior of the function, and we've got its sketch based on known data points. Now, an additional thing that I'll add here is, in this particular case, we had a whole bunch of data points that we could also plot if we wanted to. I'm not going to plot all of them, but just to point out, this coordinate here is the coordinate 1, comma, negative 20. And then we have the other coordinate, negative 1, comma, negative 50. So if we wanted to make sure that our sketch was accurate, 1, comma, negative 20 and negative 1, comma, negative 50, we would want to see if those data points seem to align with the sketch that we've drawn. And again, without the accurate vertical axis, there's no way of really knowing in this case, but I feel fairly confident with what we've got here. So I'm happy with this result and I can move on. So I do understand that this is a time-consuming process, but the steps are pretty important for you to recognize the behavior of these functions, and I highly, highly recommend that you practice a few of these in addition to the Math Excel this week. See me if you'd like clarification on any of the examples that you complete on your own. Now, to wrap up this video, let's just take a look at an applied example of this. A parcel delivery service, somebody like UPS or FedEx or even the post office, has contracted you to design a closed box with a square base that has a volume of 9,500 cubic inches. Express the surface area of the box as a function of x. So we call this a square box with a square base because you'll notice that the length and the width of this box are equal in dimension. We'll find out what x is in a moment, or at least write the function based on x in a moment. But the height y, this can change along with x. So the idea is that once we choose what x is, let's say the width of the box is 10, then we could automatically calculate y so that the total volume ends up equaling 9,500 cubic inches. If the box width ends up being 15, we could calculate y so that, again, the volume remains at 9,500 cubic inches. But rather than take the time to calculate y each time, we should be able to create a single formula that accounts for the value of y when we automatically compute the surface area. And the reason why this is particularly important is that UPS or FedEx, they may be selling boxes to their customers, and we want to be able to sell them a box that contains 9,500 cubic inches of volume once folded and taped together. But we would need to know the amount of cardboard that goes into it. And the amount of cardboard associated with this box is essentially the surface area. If we were to add together all edges of this box, the area of each edge, well, then we'd have our surface area. So I'm going to make a note of that. The surface area is the sum of all face, I'm going to call it face areas. So in this case, we have a front and a back that's identical. So the front side and the back side, those are both x units wide and y units tall. So the front and back areas are going to be x times y. The left and the right side, since this is a square-based box, are going to be the same. If I look at the left side or the right side, again, the height is y and the width is x. So in this case, the left or the right side would be x times y. And then as far as the top and the bottom goes, well, that's a little bit different. The bottom is x times x and the top is x times x. So we'll call that x squared. Now, since I have two of each of these, I've got two left and right sides, two front and backs, and two tops and bottoms. I could say that the surface area is equal to 2x squareds plus 4xy's, because I've got 2 from the front and back and 2 from the left and the right, for a total of 4xy's. Now here again, we're actually in pretty good shape. We've got a surface area based on x and y. What I would like to do is see if I can rewrite this equation so that y isn't used. I don't want to have to supply the y value. That's where the volume comes into play. In this particular case, the volume is x times y. That's our length times width times height. We also know that our volume has to be 9,500 cubic inches. So if the volume is 9,500 cubic inches and we have x squared times y, then y by itself is simply equal to 9,500 divided by x squared. And I can make that substitution over here. So now our surface area is equal to 2x squared plus 4x times 9,500 over x squared, which is 2x squared plus, and we can simplify the 4 times 9,500 as 38,000. X over x squared simplifies to 38,000 over x. And now we've got a formula, surface area, which is a function based on only the letter x at this point. And if this was a polynomial, then we can use the exact same analysis tools from so far this week to finish analyzing it and looking for specific results. However, because of this division by x, that implies that we have some sort of x to the negative first power. Well, that no longer meets the criteria of a polynomial. So if it's not a polynomial, what do we do next? So this is actually a little bit early in our discussion, but I wanted to let you know about it next week as we pick up with rational equations. We'll be able to address this concern because rational equations tend to be polynomials divided by other polynomials. And with that notion, we can account for this discrepancy. So be on the lookout for this equation again, looking for this problem in the future. We'll discuss it further at another time. Thanks for watching.